Hello students, welcome to this lecture. So we'll continue with the domino logic gates, and in this particular lecture we will specifically look into one particular non-inverting configured combinational gates and try to determine the best gate size so that we'll get a minimum delay. Right, so going forward, so this is an unfooted domino logic. So what it really means is we have the dynamic logic here, dynamic inverter, and then followed by another inverter. So the dynamic inverter, and if it is unfooted, so we will have this kind of a schematic. Unfooted means the foot transistor is not there. So the logic A or the input A is given to this particular NMOS transistor. On the PMOS transistor, it is anyways clocked. So this represents our dynamic logic inverter, followed by a regular inverter, which makes it as the consolidated structure now becomes a domino logic or the domino circuit. And notice that the domino logic or the domino circuit will always be applicable for a non-inverting configuration. So the non-inverting output. So based on the input here, I'll get an inverted output here, and then Y will be the the non-inverting output for the input A. And in this particular gate level structure, the representation of the dynamic logic is nothing but a regular gate structure of an inverter, but because it's a dynamic logic, so we have associated, or it is attached with, a clock signal, and it is bubbled, which represents that this clock signal is going to the PMOS side of the transistor. So this particular structure is cascading to the next regular structured inverter, and I've written a H here. H here represents the high skew inverter. Okay, and let's talk about this high skew inverter. So what we have seen in the dynamic logic, the dynamic logic has a problem for the when the output actually falls down. So that is a problem. So we always need a rising output, and that's why, or rather, the rising input. Because if suppose I cascade this particular dynamic logic to another dynamic logic, then if I have a the falling output, this falling output will become an input to the another dynamic inverter, and that is where the problem arises. So what we do is we have an inverter here, and so the falling output is converted into a rising output here, which then goes and feeds into the next dynamic circuit. It may be an inverter, or it may be any other NAND or NOR gates. So the falling output here is converted into a rising output here, which is then fed as an input to the next dynamic logic circuit. So in that sense, this particular dynamic logic output here, or the dynamic inverter here, we are interested only in the falling output. And the reason is very simple. If A is equal to 1, I will get the output to be falling, right? It will be go to 0. If A is equal to 0 in the evaluation mode, because this particular output node is anyways charged or pre-charged to VDD, it will stay at VDD, right? So A, whenever it is 1, then only this, the output of this dynamic inverter will go to 0, and thereby, so we will be interested only in the falling output, because the rising output, or whatever, the rising output or the high level logic will be staying or will be retained, right, in the evaluation mode. So we don't have to worry about the delay of the rising output. We only have to worry about the delay for the falling output. For the rising output, the delay will actually be 0, because it is anyways retained. So the pre-charge, it has this particular output node is pre-charged to VDD or logic level high, and it will be retained to the logic level high. So only when A is equal to 1, it will fall, and that is what the delay we are interested in. So what we'll do is, in this particular dynamic part of the domino logic structure, for this particular first stage, we will be interested only in the falling down output. So that means the logical effort for the falling down and then the parasitic for the falling down is what is interesting to us. So we calculate that. the falling down one and then the parasitic down. And anyways, dynamic logic always has, when we represent the logical effort or the parasitics, we always represent for the logic, the output going down signal. So we have GD is equal to 1 by 3, and then PD, the parasitic, is nothing but 2 by 3 for an unfooted one. And in this particular configuration, since the output is falling down, so we need, or the output here will be rising. So in that sense, if we are interested in the falling down signal here, why not make this a rising up signal really fast? And that's where the high skew inverter will be used. And a standard high skew inverter is, 2, instead of 2:1, we make this 2, we retain this 2, the size of 2 in the PMOS side. And on the NMOS side, we make the strength of the NMOS less. And, normally we will associate with, making the strength to be half that of the 2:1 inverter. And that's why we have the strength of 2 and 0.5. So the width of this PMOS remains to be 2. NMOS width is reduced to 0.5, and thereby we now have a high skew inverter. So the advantage of the high skew inverter is this is going to really be faster, right, in getting the signal to rise to a logic level high. So here we will get the output going down, and here we will get the output going up, and thereby if I make this high skew inverter, we will get a really fast output. Now, what should be the logical effort and then the parasitics for the rising up signal? So that is what GU represents. GU is nothing but the input capacitance at the input side of this particular high skew inverter, which will be 2 plus 0.5. The benchmark inverter in this case, it is a rising output, so it will be 2:1. So we will have the input capacitance as 3 for the benchmark inverter, and then the total is, or rather the GU value turns out to be 5 by 6. The parasitics for the rising up, again, it will be 2.5 divided by 3, so it will be 5 by 6. Going down, logical effort, I've just noted it here, but not really of any relevance for the domino logic. The GD will be nothing but 2.5 divided by 1.5 is nothing but 5 by 3. So considering only the rising output in the domino logic, so our overall G, which is nothing but the product of all the G's, which will be the GU here and then the GD here, will be 1 by 3, and then 5 by 6 multiplied by 5 by 6 will give me 5 by 18. And I've taken the summation of all the parasitics just because we are interested in finding out the overall delay. So the summation of the parasitics will be nothing but 2 by 3 plus 5 by 6 turns out to be 3 by 2. Right? Hope this is clear. Moving ahead. So let's look at a similar configuration, but we have a footed domino logic. What it really means is we have, instead of a unfooted dynamic logic here, we have a footed dynamic logic, makes it a footed domino logic, right? Put both of them together. So footed one will have a foot transistor, and then this will be connected to the clock, same as that of this clock, which is getting connected to the PMOS transistor. So during the pre-charge mode, this will be on, this will be off. So there won't be any contention. So the output node of this dynamic logic will get pre-charged to VDD. The size is 2 and 2, so that it becomes, the total switching resistance turns out to be R, which is very similar to that of the 2:1 inverter falling resistance. Right, again, high skew inverter is been applied here in the next stage, so that we will get a really fast rising output in the output of the inverter, in the output of the second stage. So let's try to evaluate the logical efforts. The logical effort here is, GD for the falling output will be nothing but 2 here, the input capacitance, and then the benchmark inverter is 2:1, so it will be 2 by 3. Parasitics will be 2 plus 1, which will be seen at the output of this dynamic inverter, and the benchmark inverter is again 2:1, so I will have 2 plus 1 divided by 2 plus 1, so it will be 1. This remains the same as that of the previous case. The logical effort of going up for a high skew inverter is 5 by 6, and then the parasitic is also 5 by 6. So again, so the multiplication of or the product of the logical efforts for both the stages put together will be 2 by 3 multiplied by 5 by 6 will be 5 by 9. And then the summation of all the parasitics will be 1 plus 5 by 6, which will be 11 by 6. Right? Hope again this is clear. So what we have seen so far is the unfooted domino logic and then the footed domino logic. And then we have evaluated the logical effort, and then we have evaluated the parasitics, the total parasitics. So let's try to see an example here and try to evaluate the best number of stages we need to design for the domino logic equivalent circuit or a domino logic compliant circuit, which has a load capacitance of 64 into C, where 1C represents the unit NMOS transistor's capacitance. And here the first stage sees a capacitance, input capacitance of 1. So again, so we need to find out what is the number of stages in this particular circuit, and what should be the best, or what should be the sizes of those gates or the stages, so that we'll get the minimum delay. All right. So earlier we had seen a similar kind of an example where we had the best number of stages, best number of inverters, so that we will get the minimum delay. And it was especially for the same or the exact load capacitance and then the exact input capacitance. So now the example has been changed a little bit, and we are trying to see what is the best number of stages considering the domino logic. Right? So that is the difference. And let's say that this is, I've taken this as 5 by 9. So if I go back, 5 by 9 is this particular logical effort, the product of this logical effort. The product of both of them is the 5 by 9. So it is it is a footed domino logic. And if I go back the previous slide, the G here for an unfooted domino logic is 5 by 18. Okay, so coming back to the current slide. So what we'll consider is put together these two stages. So let me get my pointer. So this will be considered as one domino logic, and let's say that we are interested in designing this whole stages in terms of a footed domino logic. So its G value, so let me put it here, should be 5 by 9, right? So I'm considering this to be first stage, and then this to be second stage, and then similarly we will have third, fourth, fifth, sixth, and seventh and eighth and all, so that we will get the minimum delay. So what we really need is an expression of the delay in terms of the n stages, and then try to optimize it. So if I consider this to be an n stages, the dotted lines will be the n stages. And G is 5 by 9, and then the total parasitics which we have calculated earlier, in the previous slide, was 11 by 6 here. So the summation of Pi is for the first two stages, so I'll write it as I is equal to 1 and to 2 was 11 by 6. So I've considered this 2 for the first two stages. Okay, and then we will keep on adding the domino logic, right? And then similarly we will keep on adding the domino logic, and the number of domino logics we will add, so that we will get the minimum delay. That is the first thing. The second thing is we need to estimate what should be the size of this high skew inverter, what should be the size of the dynamic inverter here and dynamic inverter here, and then what should be the size of the high skew inverter. So let me write the delay expression considering n stages. So if it is n stages, note that this n stages will have n by 2 pairs of domino logic, right? So n by 2 pairs, so let's say that if the number of stages is 10, that means that the total number of stages is 10. So the domino pair will be 5. So that means that we will have one dynamic inverter and followed by another regular inverter, and that will be one pair. And similarly 5 such pairs will be there. All right. So n by 2 is what I'm considering for the domino pairs. Okay. So let's try to write the delay expression, and the summation of the parasitic is 11 by 6 for one domino pair. So if I have n by 2 pairs, the overall parasitics will be 11 by 6 multiplied by n by 2. And then the overall path effort and multiplied by the n stages is what will give me the overall delay, right? So the parasitics plus the total, the path effort in the sense, the total stage effort, the individual stage effort multiplied by the n stages should give me the overall delay. Here, the number of stages is n, so that is fine. And this particular portion, what I've done here is, this is the individual stage effort, that is what I have represented or I have written. So if I closely look into this G value is 5 by 9. Okay. So we'll come to that later. 64 by 1 will be our capital H, which is nothing but the product of all the electrical efforts or the fan outs, starting from the last stage to the first stage. So it will be nothing but 64 by 1. Right. So this portion is, hopefully this is understood. The G, if I'm considering the G here for n stages, it will be nothing but the product for the n stages multiplied by all the GIs. But here we know that for the 2 stages, the first and second stage, and similarly third and fourth stage and so on, for one domino pair consisting of 2 stages, it is actually 5 by 9. So for n such stages, what we will do is 5 by 9, the square root of that, and then raised to n. So it becomes 5 by 9 raised to n by 2. So that becomes my overall G multiplied by H for the n stages, and raised to 1 by n will give me, right, the best stage efforts, so that we'll get the minimum delay. Right. Again, hope this is clear. So finally, we will get this particular expression for the delay, and we know what to do to get the minimum delay. We can differentiate this delay expression with respect to n, so that we will get the best or the optimal n value. So we'll do the first order differentiation and put it to 0. So we will get 11 by 12 here, and then this is parts of partial differentiation, which will give me 64 raised to 1 by n, and then so on. And so this expression should be equal to 0. And if I consider this particular portion, 5 by 9, 64 raised to 1 by n, if I put it as kind of an a or something, so this will also be so this I can rearrange in terms of a, some function of a. So 64 raised to 1 by n will be nothing but 9 by 5. So this I can write it here, and heuristically I can calculate what should be the a value, or what should be the solution of this particular equation in terms of a. So it turns out to be 2.809. Right. Heuristically means I will have this particular equation. Written like this: 11 by 12 plus a into 1 minus log of a, and 9 by 5 is equal to 0. And I keep plugging in the values of a as 1 or 2 or 3, and then in between that 2.5, 2.8, 2.9, and then it should equate it to 0 or whatever, the closest value that a can accommodate, so that I'll get closer to the 0 value. That will be the solution, and the solution turns out to be 2.809. Alright, hope that is clear. Once I have this 2.809, and if you remember, the square root of 5 by 9 multiplied by 64 raised to 1 by n will be nothing but our f cap value. Right, this is the best stage effort we want. Right, so using this particular f cap, let's try to see what should be the best stage, best number of stages we have to get, so as to get the minimum delay. Right, now the f cap is written as 2.809, right, and which will be nothing but f raised to 1 by n, or rather I'll write it as, because it's the best one, I'll write it as n cap. So for getting 2.809, right, what should be that n cap? So that n cap turns out to be 3.13. Right, so the n cap turns out to be 3.13, and we cannot have 3.13 as the number of stages. So, and we always want the number of stages in a domino logic to be the even numbers. So instead of 3, we will have to go for 4 as the number of stages. And if the number of stages is 4 actually, then what should be this individual stage efforts, which will be nothing but 5 by 9, 64 raised to 1 by 4, right? The square root of 5 by 9, because that is the individual stage will see. If I have domino logic, each of the stage will see square root of 5 by 9. And because the load is 64 and an input capacitance is 1, so we will have the 64 raised to 1 by 4. So the F cap, the best stage effort for the individual stages, turns out to be 2.108 instead of 2.809. So this will be the best stage effort we can see for a domino logic, right? So if I use this on the individual stages, then I should be able to find out what is the best gate size, and from the gate size we can easily find out what is the transistor size, right? So the best gate size, I can find it out by equating this GI HI to that of the F cap, which is 2.108. So GI HI for this particular inverter is nothing but 5 by 6, because this is a high skew inverter, multiplied by 64 divided by X dash. So that is the size I have taken here. So X dash turns out to be 25.29, and this is the gate size, or it's basically the input capacitance for this particular inverter, regular inverter, which is a high skew inverter, all right? Similarly, if I want to find out the X value, which is nothing but the gate size of this dynamic inverter, I now know the X dash value, and its GD value is 2 by 3 multiplied by 25.29 divided by X. It will be nothing but 2.108, right? So this is nothing but coming from our F cap value. So X turns out to be 8. So this, for this dynamic inverter, the X or the gate size is 8. So we have to appropriately design the transistor sizing for this dynamic inverter as well. This particular high skewed inverter, again, I have given a size of Y dash, and we need to find out Y dash. We know 2.108 as the stage effort, and 5 by 6 multiplied by 8 by Y dash will give me, Y dash as 3.162. Again, it's a high skewed gate size. So the overall delay in this case will be nothing but, so 2 multiplied by 11 by 6, because there are 4 stages, and 11 by 6 will be the parasitic of one such dominic pair. So that means 2 stages combined, we will get 11 by 6, and then we have one more domino logic pair. So we will have 2 multiplied by 11 by 6 plus 4 number of stages multiplied by the F cap, which is 2.108. So we will get 12.09. So the overall delay turns out to be 12.09. And if I closely look into the regular structured inverter, we had the minimum delay as 15. Here the minimum delay turns out to be 12.09. Right, so there we obtained the minimum delay of 15 using 3 stages. Here with the 4 stages, in fact 2 pairs of domino logic family, we are getting a delay of 12.09, which is less than that of the 15 value, which is an absolute, which is a normalized delay value, not an absolute one. So if I want to find out an absolute value of the delay, I have to multiply it by 3 RC, where and if we have the RC value as 1 picoseconds, we can calculate the absolute delay. So hope this is clear. The sizes of the transistors. So because we have the sizes of X dash as to a 25.29. Right. So what we will do is, this is a high skew inverter. So high skew inverter. So what I had written was a high skew inverter, and if you remember, the sizes was 2:0.5. So what we are going to do is, this particular 25.29, we are going to divide it into 2.5 parts, where 2 parts will go here, right, and then 0.5 parts will go here, right, and that's why we get 20.23 and 5.05. And similarly, the X value for the dynamic inverter, which is nothing but the gate size of the dynamic inverter was nothing but 8. So 8 will be put in here where the input is connected. And for the foot transistor, it should be similar to that. And then for the PMOS side, we will take half of it, right? And this one also, we will have whatever is the value we obtain of Y dash. We will do 2.5 parts. 0.5 parts will go here on the NMOS side, and then two parts will go into the PMOS side. Lastly, the size, the gate size is anyways 1 here. So we will have 1, 1. So this particular size, the size of the dynamic inverter here in the first stage, if it is the size of 1, the clocked PMOS transistor should have a size of 0.5, so that we will have this particular parasitics to be 1.5, and that will that will give me the 1.5 will be considered appropriate. So if you remember, we had a size of 1 here, and then a size of 1 here, 2 and 2, right, which gave us the parasitics of 3 capacitance, and then divided by the parasitics of the 3 capacitance gave us the normalized parasitic as 1. So here it should be 0.5 instead of 1.